Thanks, Mark, and thank you everybody for the opportunity to speak. I'm going to talk about seismic. So we've been shaking the ground up at Tarcoola. This survey has just been completed, so the interpretation that we've just done on this data is literally hot off the presses. So this is the first look at what we've found so far. You can read that one at your leisure. Download it off the website if you're really keen. A few acknowledgements. Firstly, I'd like to acknowledge HiSeis, who have been our partners for this work and been involved right from the start, from planning right through to acquisition and interpretation. In particular, Alastair Tate, who's done the initial interpretation that we're going to have a look at some of the line work for, and that's obviously a work in progress. And also to Tom Harris, who's been our consultant geophysicist from Merlin Geophysics, who's helped us all the way through. And finally, to the Department for Energy and Mining. This survey was a result, or came from, an ADI co-funding grant, and we thank them very much for that financial assistance. Because I tend to waffle sometimes, I'm going to start with the end, otherwise we might run out of time. What are the key findings? Well, I'm going to be very brief, and we'll go through this in the presentation. The seismic has shown that at the Tarcoola region, the earliest deformation we see is a north-south directed broadly shortening that's thrust ramped up the stratigraphy, caused a broad folder architecture, and then developed a thrust duplex on the southern preferentially orientated limbs of those thrusts. That thrust architecture has then been overprinted by an array of faults in what would have been traditionally called the D2 deformation, west-northwest, northwest trending and northeast trending faults. And we can relate the Perseverance fault, which is one of the significant structures at the mine, and we'll look at that. And we can get a pretty consistent fault chronology out of that from the seismic. So this one just shows the seismic section up in the top right, which cuts across from the Perseverance mine, and we can see the Perseverance shear truncating that reflector unit, which is the Fabian quartzite. We'll get into all of that. We can also relate similar structures as Perseverance shear onto the regional seismic, which is the lower image, and that's the Geoscience Australia line. And we can see similar structures out to the west. Some of those are coincident with known gold occurrences, and others have not been tested, so they're very exciting areas for us to follow up. A brief location, if anyone doesn't know where Tarcoola is, it's located in the central Gawler Craton. It's about 750 kilometres northwest of Adelaide, in the Wilgina Domain, which is a mixed package varying from Archean right through to Hilteborough Age intrusives. One of the features of the Wilgina Domain and the central and western Gawler Craton are regional scale shear zones that define the boundaries of the domains, but also host significant gold mineralisation. And you can see on the southern part of that image, the Yalbrinda shear zone, which hosts our Tunkilia gold deposit. That's been a focus of our recent drilling work. And if you look around Tarcoola, our exploration licence there, you can see a big northwest trending fault, the Lake Labyrinth shear zone, which hosts significant gold mineralisation as well. I don't intend this to be a geology lesson, but it is useful to look at some of the rocks before we look at the seismic. So this is actually a view of the Perseverance pit looking to the northeast. The oldest rocks we see in the pit area are the Paxton granite. They're about 20 million year old Monzo granite. Overlying the Paxton granite is the Tarcoola Formation. It's a 1650 broadly aged sedimentary package, sits non-conformably on the granite, dips gently to the southeast, and has been subdivided into three members. There's a basal conglomerate, then the Fabian quartzite, and then the Sullivan shale. And the Fabian quartzite is the one that we really see in the seismic the best, and we'll have a look at that. A plan view, this is really just to demonstrate in plan. You can see that all those colours, that's just showing the gold distribution. It's basically the maximum gold from each drill hole in the historic database. I'm highlighting here really two structures to look at and keep in mind when we look at the seismic. That thick black line is the Perseverance shear, Perseverance Fault, cutting through the Perseverance pit. And that light green one, hopefully you can see that okay, is what was termed by the mine geologists, the WPG mine geologists, the granite vein. The pit follows the granite vein. Those pink lines are the granite contact. So there's still remnant resources at Perseverance, and we're interested in looking at those. And the question arises as to where do these structures continue? Do they continue? Well, what do they do at depth? Particularly to the north, it disappears under cover. We've flown detail magnetics, but the Tarcoola Formation itself is non-magnetic, so it doesn't really help to trace these structures. So the thought turns to seismic. Seismic has one advantage over potential field methods in that it can see deep, but it also can see deep without a loss in resolution like the other methods. But that's if it works. We know seismic can be challenging in a hard rock environment. In our favour here is that the Tarcoola Formation basin is low metamorphic grade and is fairly well preserved and reasonably gently dipping. So if it's going to work, it'll work here, if anywhere, in a hard rock environment. We're also lucky in that we had a test case in that green line, which is the regional Geoscience Australia seismic line. So that runs from the Eastern Goldfields in Western Australia right through to Tarcoola. And we engaged HiSeis to reprocess that data, because it's obviously deep crustal seismic, to try and see if we could enhance and depth convert the data, but enhance the shallow structure. And you can see in that image there that we can see the dipping reflectors, those red lines on that front image, and you can see the Tarcoola Formation. And we also managed to get quite a bit of structure out of that we think does correspond with known gold occurrences. Given that encouragement, we decided to undertake additional seismic. So we've done 5 lines of seismic, 40 line kilometres in total. The eastern line there runs immediately through the mine area, and then we've got lines at 2 to 4 kilometre spacings further west, so we can tie it in with that regional Geoscience Australia line. This is the acquisition in progress. This is at Tarcoola itself. That's the HiSeis recorder truck. Everything was controlled from that truck. So the vibe shaking, everything, the recording, the quality control. All the geophones were wireless nodal systems, so as soon as those geophones were laid out, the system's live, and then they're all gathered at the end of each line and data harvested. The only real challenge there was we're on the Trans-Australian Railway line, and so there were a lot of passing trains, and we had to pause the survey each time a train came through. It's probably a good source of passive seismic energy, but noise for us. So this is out on the line. That's the Vibe truck on line 1, and that's the survey specs there you can see. The bottom left shows a picture of the weight drop. We used that on the southern end of the first line because we couldn't do line clearing. And obviously traffic control was an important factor, given that we crossed the main Tarcoola road quite regularly on each line. It's a 20-second sweep, single sweep, taken, reading from 4 to 120 hertz. That's the processing workflow. I won't go into that in detail, other than to say, after static corrections, the really important part was all the velocity modelling to get the stacks right. We had time migrated stacks, and then the depth migrated stacks are what we've done the interpretation on, and that's what we'll look at. Quick look at the velocity model that was produced with seismic tomography, and this is really fascinating, and there's a lot more information to be got out of this. Top left shows a perspective view of the 5 lines overlain on the Geoscience Australia line. You can see the northern ends of those lines are showing quite strong velocity highs, tomographic highs, and they match beautifully with the known granite from mapping and from the magnetics. The westernmost line also has picked up the other granite body. We're also seeing other concealed granites that are not exposed, and even on the southern ends of the lines that we didn't even know about. We think those are probably granites, or even possibly the Harris Greenstone belt offline. The bottom image shows just the velocity section for line 1. And you can see it's really well imaged in the centre, the main Tarcoola Ridge, which is where the old original blocks mining area was. And we're also mapping quite nicely the granites on either end, as well as some of the dipping stratigraphy. And some of those scallop lows also correspond beautifully with major structures we can see in the magnetics, and we can trace them through. That's the seismic data itself. That's all of the PSDM sections stacked onto the, or rather in perspective with the geoscience line. I really just want to show here that you can see really good correspondence with that westernmost line in particular, that you can see with the dipping Fabian quartzite unit matching really nicely the reflectors in the Geoscience Australia line. And also it's mapped the granite contact quite well. We'll take a quick look at line 1 in the time we've got. We can only really look at one, and that's going to be the one that goes across the mine area. So it runs immediately north of the Perseverance pit and across the Tarcoola Ridge, and then continues for another nearly 4 kilometres south of the rail line. So that's the seismic. You can see those red reflectors that are highlighted there. So the earliest thing we see here is this north-northwest directed shortening. This has formed a broad fold structure, an asymmetric fold structure with the south dipping limbs and a parasitic fold. Continued deformation has then caused thrust stacking of that package up against the granite at the Tarcoola Ridge. So we get a series of these thrust flats and then these steeper ramp structures. So that would equate to the D1 in the old scheme. And that matches quite well the existing interpretations that were done. And that's an Anglo gold section shown there, showing a very similar geometry. What we then see, which we haven't really seen before, are these shallow structures, northeast trending, northwest dipping structures that truncate those reflectors. We sort of expected that those reflectors would continue deeper, but they do seem to be truncated. They may be offset at depth. These overprint, obviously, those D1 structures, and we can also image at this time vertical structures, one of which matches perfectly with the modelled position of the Perseverance fault, and that's simply just taking the wireframes from the mine and extending them. So we think the Perseverance structure has come in at this time. It's overprinted by those northwest dipping faults, but it also truncates a lot of those faults, and we think there's a common timing between those two structures, those two orientations. We then see steeper northeast trending, northwest dipping structures. So that green structure that you see in the top right-hand corner, that would be the position of what's been called the basement fault. That's a major sinistral fault to the west of the mine. And we also see northwest trending faults as the last structure really, or the major structure, apart from some narrow vertical structures that could be dikes or reactivated early thrust structures as well. We'll skip line 4, we don't have time for that. So this is a perspective view showing all of the lines and the line work that's been generated from this interpretation. You can see the northeast trending structures. The basement fault is one of them, but there are several other structures. And there's some pretty significant structural intersections there, and they match really nicely with what we've interpreted from the magnetics and also what we see on the ground, and those timings match what you see on the surface geology. And in particular, some of the best gold anomalies, particularly out to the west, correspond with some really interesting structural intersections on those northeast faults, and they share a similar footwall association and hangwall association with the early structures. But more importantly from us, there are other very similar structural intersections that are completely untested or undercover. So, short and sweet, the conclusions, we really have just got this hot off the presses. We've got lots and lots of targets to follow up, but we've been able to put it into a consistent kinematic context, and we've got a lot of faith now that we can map these structures to great depth. We can see which ones are the deep tapping structures, and we've had Hildeberg intrusives as well, that we think these structures are tapping, and it's now for us to basically pull it all together and start tracing these structures and get out and truth test these with the drill rig. Thank you.